Okay, so then I will make a question. So what is an image? It's a function. Okay, as a this one. Okay, this is a function, that's good. What else? So if it is a function, I like using the whiteboard. It has a domain and a range. That is something general of functions. So all functions have a domain and range. Okay, so let me. Okay, so let's start a new whiteboard. So an image is a function. So when you see something like this and you have here your object, so what you have here, actually, you have to set your axis. So you put this is y, this is x. It depends on the conventions, but this is a typical convention. You have to say where the origin is. So let's mark the origin. Use this one. So this is the origin. So that means that is the 0, 0 coordinate. And then in one dimension, let's say that we have. I'm thinking which letter to use. Okay, I'll use two of them. So I'll use n and I'll use m. And then here I will also use it x dimension and here y dimension. So that was what I was taught. Which one to use? So if we have n pixels in the row, we go from 0 to this. The first one, this is xy. So x is the first argument. So we go to n minus 1, 0. This would be this pixel here, the n. Sorry. This would be 0, n minus 1. And this one here, would be n minus 1, n minus 1. And the same, instead of using n and n, you use x dimension, y dimension. Okay, so for every point here, you could say what is the color of that image. So that is a function. So an image, let's use a different one. So an image is a function that goes from, so let's make it general first. So a function in general takes arguments when you say y is equal to f of x, and x is a vector, y is a vector. So what we are saying is that, let's put it simple. Okay, so let's say that this is R n, this is R n. So here you have n real numbers, here you have n real numbers. So this is a vector of dimension n, this is a vector of dimension m. So in general, a function has something that is called a domain. So this is called a domain. So this is where the function is defined, and this is called the range. In general, you are used to range. You are used to think of these functions as, I will use different colors again. So this is, let's say this is yellow. So you go from an X domain, that is, in my example, it is Rn. So this is the X domain. You transform this by a function onto transform it into range. So here we have y. That in my example was Rm. Okay. So this is in general, and in general you write this function like this. So you say f is a function that takes values from Rn and transforms them onto values of Rn. Okay, so what is an image then? So an image is a function that translates values spread all the time, or being changing colors all the time. So I is a function that takes xy coordinates belonging to R2 and transforms these. Let's change colors. So now they are transformed onto R3. Why R3? Because we have RGB. Okay, so we can think of an image as a continuous function. So it is continuous because the domain, the range is continuous, and the range is continuous. Okay, but we said, so this is the kind of analogical images that we were discussing yesterday. Do you remember yesterday that we studied? Okay, there is an image in the real world. This is the image in the real world. So the image in the real world, for every possible spatial location, transforms it. It gives you what is the color. Okay, so this is let's just write it there. So this is the real world image. This is the real world image. But we do not have real world images in the computer. So in the computer we said, okay, we are discretizing space. So that means that this xy cannot be a continuous. Cannot be continuous variables. They have to be discrete. Okay, so let's say that we go from 0 n minus 1 to so we say now x and y belong to I will write it like this. So 0, 1 all the way to n minus 1 Cartesian product with 0, 1, n minus 1. So now, and this goes into R3. So this image there is the one that has been quantized space quantization, space sample, we call it, right? You can use both words, but just to keep quantization for colors and space, and sampling for space, to try to be consistent with the use of words. So this is the space sample image. So now we don't allow any possible coordinates. We only allow coordinates that the first argument is taken from this set, the second one is taken from this set, and the output will be color. Okay, but now we have to discretize colors again, because we know that with the computer we cannot represent infinitely many colors. So we don't allow any possible color, but we only allow colors that are in the range we use. So I will explain now the difference between these two. So we only allow this one. And we will use, so each one of the channels, the RGB channels, they go from 0 to 255. So that means that is cubed. Okay, so it is this set 3 times. Now, on the other side, we also have the same. So also have 0, 1, and minus 1, 0, 1, and minus 1. Let's use this one. That's it. Okay, so let's have a look at it. So an image, let's put a name. So this is sample, and quantize. So quantization of colors. So quantization is this one. So sampling refers to this discretization, while quantization refers to this discretization. But then it is a function. What else? Yeah. So what is the difference between this kind of parentheses here? So this is the difference between using 0, 1, 255 and 0, 255 and 0, 255. Okay, this you already know. So these ones here, these ones means including, so 255, we call these sets. So this is S1, S2, S3. So here 255 belongs to S2, while here 255 does not belong to S3, okay, because we are using the closed brackets on the. So here it is closed to the right, here it is open on the right. Okay, what about this one? So why using curly brackets for that? There's a difference between these three sets. So what about 0.5? So 0.5, the question, does it belong to S1, to S2, so to S3? Does it belong to S3? Yes. So these are all possible values, real values of 0.5. So that's. What about S2? The same. So the only difference between S2 and S3 is the last point. What about S1? Doesn't. Because these are only the integer numbers between 0 and 255. So that is the difference. So this is a discrete set. This is discrete. While these two are continuous. Okay, so that is a matter of notation. Okay, so we come back to our images. So now we know an image is a function. So let's put it like this. So, and we may specify different kind of functions. So we know we can define all these functions. So one is in the real world image, the other one is the one that is sampled and sampled in space, and this one is the one that is sampled in space and colors. So the colors are quantized. So this exists in the real world, this exists in the computer, and the three of them exist mathematically. So mathematically, you can work with the three of them. Okay, very good. Then, more questions from your side. What about videos? Is it the same? Now we want to define a video. Define a video. How would we define it? How many arguments do you need for a video? 3 arguments. Okay, so which are the arguments? Right? Okay, so time, x and y. So give time, x and y. Now, this is a function that goes, that I will normally work in the continuous. Actually, mathematically, it is much easier most of the time. We will be working with the real world image, even if we don't have access to it. But it is much easier to think in continuous terms, because everything is much more mathematically tractable. So all these differentials, even if you think that differentials are integrals, are more difficult objects or operations, they are actually simpler than sometimes the summations. So in general, I will refer to the continuous images. So this is a video. What about the volume? We have a map. So let's say that we have, instead of an image, you want to represent your brain. So now we have here, this color. So we have 3 axes. Let's say this is the convention. I will use my own convention. So this is y, this is x. So now you want to represent your brain here. This is your brain. Okay, so for every location, you have a different gray value. And now we have a volume. So this is a video. Now we have a volume. And how many coordinates do you need? You need 3 coordinates. You need x, y, and z. Y, and z. So mathematically, actually, videos and volumes are the same. So they are the same kind of objects. Okay. Yeah, if now you make your volume change over time, now you can add an extra coordinate. So I want to make a video volume. Video volume. Now I have time goes from R4 to R3. That is your question, right? Yeah. So from the point of view of mathematics, a video and a volume is the same. Actually, there are many tools that are borrowed from each different domain. So people working with volumes, from time to time, they discovered that people working with videos, they're doing something very nice, and they borrow what they and vice versa. Okay, and what about signal? So you have a signal, that is the one the signals that you have word. So you say this is x of t and this is my signal. So this is signal. The signal is simply taking an R value, transforming it. So I think everything are functions. So these are called one-dimensional signals, 1D signals. These are called 3D signals. This is a 3D. What else? An image here is a 2D signal. So when we say 2D, 3D, and this is a 4D signal. So when we say 1D, 2D, 3D, what are we referring to? Why do we say 4, 3, 2, 1? where are we taking this number from? From the dimensions of no. So there are two dimensions there. We have two dimensions.
From the axis
Of the
function.
It is undefined. I'm trying you to be precise, okay? So that is what I'm trying to get you. In general, you have to be precise with the language. So the dimension of a function, that is not well defined. So a function is an operation that takes elements from one set and transforms into elements of another set. It doesn't have a dimension. So who has a dimension? The domain has a dimension. And the range also has a dimension. It may not even have dimensions, so not all functions transform vectors from one dimension to vectors of other dimensions. There are many other kinds of functions. But the ones we are interested in, we are taking this number here. So this is the 4, this is the 3. So when we say that this is a 1 designant, we are referring to the exponent, this one here that we haven't written, but this one. So the 1D, 2D, 3D, it borrows number from the dimension of the domain. Okay, that is what the word you were missing. And think in an exam. If you write in the exam, an image is a function that borrows the dimension from the dimension of the function. That is incorrect. Because it borrows the dimension from the dimension of the arguments of that function, or the domain of that function. Okay, very good. Okay, good. Then, yeah, so when we talk about 3D signals, we only refer to the dimension of the input, not the dimension of the output. So the output, it is undefined in this name. So if you want to say, no, it is 3D, then you say a color 3D signal or a grayscale 3D signal. So in a grayscale 3D signal, so for instance, you have seen the images from the brain. So for instance, if we look at this, so let's say, and we look for images. This one here are slices through that volume. So this is, in this direction it is Y, in this direction it is X, and then each one of these images is a slice. Slice is set. So we are going through set, so we are going in this direction, and then for each one of the sets we are representing X and Y. And this is a possible representation. Another representation, I'm sure we have some kind of isosurface somewhere. If not, I write isosurface. We will get to what is an isosurface like. This is another kind of representation of the same kind of information. So we have a volume. We have X, Y, Z, and here we have a mixture of representations. So we have removed part of the information, and then we are seeing the gray values side, but then we are plotting somehow just a surface on that. Okay? We can also do the same in images. So let's say so let's say I look for a cat. Okay, so I have an image of a cat, and then I have X and Y, and for every point I have what the color of the cat is. But I can also draw a kind of isosurface here. Right? I can draw a line delineating the cut. Okay? So that line is the equivalent of this surface. Okay? So the cut is 2D. The cut is 2D. The iso line is 1D. But the brain is 3D. So the iso whatever is the surface. So it has always one dimension less. You see? Okay. More questions about this? Yeah.
And why did you?
Your name?
Belén.
Belén.
Why did you take into account the dimensions of the input and not from the output?
It's simply by convention. So by convention, when you talk about a 4D signal, a 3D signal, a 1D signal, you are referring only to the input. And if you want to specify the output, you have to say it explicitly. So it is a color, and then you know, okay, if it is a color 3D, then I know that the output has to be 3D. Also something very interesting. Okay, so let us try to describe this cut. So what is the function of that cut? Let's be continuous, okay? So let's be continuous. So the image of the cat takes xy arguments. So it goes from x2 to the cat was color. So what is the range? R3. So this is R3. Okay, what about the volume of the brain? So let us go back to the brain. The one I know. This is the one I know. So yeah, this you understand these colors are meaningless. So this is just like coloring whatever. Okay, so these are not the true colors of the brain. So this is simply a representation of kind of the density that you have there, or the kind of matter that you have there. And so how many colors can you see here? And this green, for instance, is meaningless. So it is a region in the brain that they want to highlight. It doesn't mean that that part of the brain is really green. So what is the information that we have in the brain in this kind of images? One, just one. It goes from very dark to very white, and it has a single value there. So the map of the brain, this is said, it goes from R3, but just in one color. Have you heard hyperspectral? That word is new for you. You see? Yeah. No one heard ever this word. Okay, but you are clever people. So hyperspectral is made of two words. Hyper and spectral. So what is a spectrum? Spectrum of colors, and more general, a range of what? That is more related to the spectrum of colors. No. Actually, that's. I'll come back to that. Okay. Remind me if I don't. So spectrum of. So what is a color? Why do we see different colors?
Light.
Okay, because we have light, we have photons, Why do we have, I don't know, black photons? Or black photons is a very bad example. White photons, yellow photons, blue photons. What is the difference? The light? No. The reflection. Reflection is a property of materials, not a property of light. The wavelength is different. So actually the spectrum refers to the wavelength spectrum. And you know, yes. Fine. Yes. Probably this is a nice image. Okay, so the colors are different because they have different wavelengths. Why black is a bad example? It doesn't have a wavelength. Why doesn't have wavelength? So what is black? When you see something black, what is happening there? No photon is coming from there. So it is the absence of photons. So it is not a color. So black is the absence of photons. And that brings us to the intensity. So what is intensity? The presence, but presence is yes or no? The amount of photons. So intensity is the amount of photons. So you can have a very deep blue, or you have a very bright blue. Bright and dim refers to the number of photons coming from there. So yeah, that refers to colors, but we have also infrared, we have microwaves, we have, I don't know, radio waves, we have X-rays, we have ultraviolet, and all of them are photons, but of different wavelengths. So now, hyper, what is hyper? Many, or too high, yeah. So many or too high. So hyperspectra, what does it mean?
That it has too much a big wavelength.
Could be. If you don't know the word, could be at least an interpretation of that word. What it actually means, we said it yesterday. So you have an object. Say you have an object here. Same object as yesterday. So you have an object. You have a source of light. In our case was the sun. So we have the sun here. And the sun has a spectrum. So it has a spectrum. So if I put wavelength, here are short wavelengths and here are wide wavelengths. So I don't know what is the spectrum. Let's say this is the power spectrum density of the sun. I don't know how to draw it. Let's say it is like this. So what is infrared there? It is on the left or on the right? We will try to put a couple of points here. So infrared and ultraviolet and visible light. So where is infrared? On the left. Everybody agree? Who votes for the left? You. 2 votes. 3 votes. Okay, who votes for the right? 1 and 2. Infrared has to be here. Why infrared has to be here? Because it is wide wavelength. So if it is wide wavelength, has to be on the right. And then here we have ultraviolet, here we have visible, so on. Okay, but now, so actually that means, this spectrum means you have photons of all these different kind of lights. So all these I will put it like this. And then ultraviolet, I will use violet. Use like this. And visible, I will use green. So we have the whole spectrum. So that means that we have many photons coming from the sun at this wavelength, but we also have photons coming from the sun in the ultraviolet, and we also have photons coming from the sun in the infrared. Actually, when you get heated by when you go to the sun and you are warm, it is because of the infrared, because of the light waves. Okay, good. Then, why not? So, all these lights are emitted by this one. All these photons are emitted. Reflection. Who mentioned reflection before? What's your name? Christina. So reflection is a matter of is a property of materials. It's not a property of light. So if I have a black jersey, it has a property of not reflecting light. Okay, so then why don't our eyes, this is an eye, so our eyes are tuned to receive this kind of wavelength. But why not designing sensors that can see other kind of wavelengths? We can design all these sensors. And actually, these sensors, I will draw the spectrum again. You can divide the spectrum. So you can divide, let's say that this is the spectrum. This is always that you make a drawing, a diagram like this. You have always to label your axis, okay? So this is the wavelength, this is power spectra as a function of wavelength, and so on. If you don't label your diagram, that diagram is useless. Okay, but then that means that I can design sensors that see different bands. So I can put different, I can put different eyes, which one of these bands. So when we said yesterday, we have an RTB. What is an RTB? RTB is just choosing 3 of these bands. So we are choosing this one, this one, this one. By the way, what is red? These 3 bands, which one of the 3 is red? The one on the right, because it has to be closer to the infrared. And which one is blue? The one on the left. So this has to be, and this has to be green. So RGB is just choosing 3 bands of this spectrum. And why not designing any other bands? And if I choose, I don't know, 10 bands, I can define an image. I can define an image that for every location goes to R10. I go to 10 dimensions. I see now 10 colors in 10 frequencies, 10 wavelengths. So this is hyperspectral. It is very much used in biomedical sciences. So you can design sensors that can see at any wavelength. Actually, infrared. What do you think can be used for in biomedicine? What is the property of infrared that doesn't have visible light? Transfers more heat. Actually, we have to think about that. Actually, yeah, that's very nice. That's very nice. Let's say we have an X-ray photon. We have an infrared photon. Which of the two brings, yeah, actually this gets very interesting. Which of the two brings more energy? Which one? Infrared. Okay, everyone agrees with that. Everyone. No one disagrees. Sorry? So which one of the two photons, we have X-ray and infrared photon, which one of the two brings more energy? The infrared. X-rays. Why? It's smaller. It's more long. Short or long? Shorter. Yeah, actually that's correct. So the energy of a photon, a single photon, is the Planck constant and divided by this, or also we can see it like this. Okay, so frequency actually, yeah, the speed of light is involved. So let's say, and I don't know in which way, so I'm not sure. I think it is like this. Okay? But just in case I'm wrong, so take this one I'm sure, and this one I'm sure. Okay, so this is the speed of light divided by the width. Okay, so you said before, it was you, I think, that infrared gets us more warmer. That's true. That's true. It is true. But it is not because they have more energy. So why do we get warmer with infrared than with X-rays? Because what? But X-rays is faster. So X-rays should burn more. Because yeah, there is a second. So these photons are more energetic. So that's actually why they are harmful. So they are more energetic, but they seldom interact. So they go so quickly that matter doesn't have a chance to interact with it. Okay. So they go so fast. They all go at the speed of light, but they vibrating so quickly that matter doesn't have time to get into resonance with it. So they don't interact, these ones, and these ones interact. So these ones are absorbed by matter, while these ones are less absorbed by matter. Actually, that is why X-rays, we use X-rays to go through our bodies, because they don't interact with matter. Only a few of them interact, and that is what we see, the difference between the flags that interacted with us and the flags that didn't interact with us. So infrared. Infrared interacts more with matter, but it also has a different property, that visible light. Now we are comparing to visible light, and that is another effect here. So one is the interaction with matter. The other one is here. It's the spectrum. How many X-ray photons? Where are the X-ray photons? X-ray photons are here. How many X-ray photons the sun is emitting? So many. Compared to how many photons are emitted in the visible range and in the infrared range. So there are many more photons here and here, and these photons don't interact with matter, and these ones interact much more. Okay, so now we are distinguishing between infrared. Okay, by the way. Okay, so let's continue. Then we were distinguishing X-ray from infrared. I don't know why I said infrared and visible photons. So, what is the difference between infrared and visible? What is the property of infrared photons that visible photons do not have? Why can I not see inside you? So there is light, there are photons, they go to you. Why don't I see inside you? They don't pass through. So what does it mean? They are reflected. All of them are reflected. Only mirrors, and some of them are absorbed. So there is when a photon arrives so let's say that you have this surface here. So a photon arrives, so let's say this photon arrives to here, can do two things. So one is, it is reflected, the other one, it goes through for a while, and then it is absorbed. And there is a third possibility, that is, it goes through for a while, and then at some point it is reflected, it bounces back. It is actually, the effect is, it is absorbed and remitted. And it is remitted with a different wavelength typically. Okay, so I don't see your inside because photons don't get through. What about infrared? What is the difference between infrared and visible light in this respect? It goes in much more. So they're also absorbed. They don't go infinitely inside, but they go much deeper, much deeper. So, and if they go much deeper, the biomedical engineers, what can I do with those photons? And they are re-emitted much later too. So what can I use these photons for? To see inside you. So I can put a infrared lamp on you, and then I will see not too much, but half a centimeter or about a centimeter inside you. So I can see skin lesions, for instance. They are very well seen with infrared because they go much deeper than visible light. And that was one thing. I wanted to say something else and I forgot. Okay, yeah. So these sensors, what is the name that you have used for these sensors in the courses you already know?
What sensors?
These ones here. So if I want to select a band in a spectrum, what do I use? A band pass filter. So these are, each one of these are band pass filters. Yeah, I think we have covered most of it. Okay, so there is another topic that typically causes troubles. That is how to represent colors. I have discussed that in the videos. but let's discuss it here again. So let's say that I have an image, a very simple image. I want to represent this color here. So now we know, okay, this, if I want to be precise, this goes from 0, 1 to 3 squared. So this is 0, 1 to 3, this is 0, 1 to 3 squared, because I have two dimensions of the same size. And then my range goes into something. Okay, so what is this something? So this something is typically the RGB. So this is the RGB that belongs to 0 to 55 cube. Okay, so that typical representation, this one here is called true color. What about this word? Would you agree with this word, true? Would you say that is true color or not? So why not?
You can always get the real color, I mean, it's not representation.
Yeah, so we have quantized colors, and colors actually they don't go from 0 to 255. Well, if I want to describe a color, I would really have to say it in the physical way. I would have to give you the spectrum of that color. So actually that is also very interesting. What if I want to describe a pure blue color? So I want to say I have very, very blue color, very pure blue. The purest blue, or the purest red, or the purest green you can think of. It is the spectrum. The purest green light that you can think of. What is the spectrum of the purest light that you can think of?
A line, because the wavelength is very small.
There is a single wavelength that is green, and then we have a delta function. This is a delta. Can you think of something that emits kind of this kind of spectra? The white color, very interesting too. We will come back to white later. So you think that white looks like that? Okay, if you think so, that's fine. We'll come back to that. Anything else, but white is not the device. We think the wall, the white wall, emits like that.
When red and blue are 0.
Red, blue, and
When red and blue are 0.
yeah, but that is in a monitor. But can you think, actually, looking at that spectrum, something should come immediately to your mind. The delta, yeah, that is mathematical, but in real life, what is the device that emits like that? The LED. Close to, but a very high quality LED. Laser. This is a laser. And what is the difference between a LED and a laser? So this is actually the quality of this. So a LED is more like this. So it is close to green. It tries to be green, but it is not extremely precise. And a laser is like this. A laser is really, really narrow. So a delta is just a mathematical representation. Delta functions do not exist in physics. So in real life, we cannot have a delta because delta, the height goes to infinity. So that is fine for mathematics, but not for physics. And so this is a laser. This one is a laser. And this one here would be a LED. Okay, good. Now white. This is a spectrum of white light. Lambda. This is the spectrum of white. Okay. true definition of the mathematical representation of y. Flat. Actually, you say white noise is like this. So white, so this is the wavelength of red, this is the wavelength of blue, and when you see a white t-shirt, what you are saying is that, okay, it is not completely flat, but it is sufficiently flat. Okay, so it is emitting light at all frequencies. So black is the absence of photons, white is emitting many photons in almost all frequencies, and more or less the same amount. And a laser is just a delta. Okay, so now we come back to our question. So if I want to describe color, physical description of color, I have to give you the spectrum. That is, but what about I see a wood table? What is the description of wood? If I want to describe a wood, this is the spectrum of a wood table. How would it look like? We don't know, but okay, so wood looks a bit like red, so it will have something like this. Okay, so it has a bit more photons coming from red, a bit fewer photons coming from blue, and I don't know what is the shape in between. But we can analyze the color. So when you would say colors are this is a color. When we say true color is simply, okay, I have to quantize the colors. I will have 3 channels here. I will have 3 channels. I will have 3 channels. I will have the red, green, and blue, and then I will measure how much intensity I am measuring in the 3 channels, and then I will scale that to 0 to 55. So there are a lot of operations in between. So this is not really a true color. A true color is this spectrum. What I'm representing here is just, when I say, for instance, for this particular color, we could encode it like 250. I will put it here, 255, and this is halfway. So let's say it's 120, and this is also halfway. This is also, let's say, 120. Okay, so this color here, because I'm representing that table, this color here would be 128, 128, 155. This is not color. This is just a representation of what is happening in my sensors, in my camera.
What are the same blue and green?
Why? Yeah, you mean that this one should be higher? Yeah, you're right. So this one, and then say 27. You're right. This one should be higher because it has an area that is larger than the other one. Okay. But this is very inconvenient to represent. So how many numbers? If you have an n, let's say you have an image that has use n here, n here. So that has n pixels. So how many numbers do I need to represent this image? Numbers in the computer. How many numbers do I need? This one. How many pixels do I have? N times n, right? How many numbers do I need for each one of the 3 numbers? I will need this multiplied by 3. Okay, so now, this is very inconvenient. This is a lot. So let's say if I have 1,000 times 1,000. So I have million, so n, let's say it is 1,000. This is 1,000. So I would need 3 million numbers to represent that image. Those are a lot of numbers. can I save some of them? Can I reduce it to a third of that? I can. And you know already the answer. You have watched my video. So. Yeah, but then I don't have colors, and now I have gray space. Or I didn't understand.
Yes, and if you want me to say, I don't know.
I want the same in it, or approximately the same in it, but now with fewer numbers. Fewer numbers. So I increase the pixels and the number of pixels. Okay, that could be. So you make some of the pixels equal. Actually, that is the point. That's the point. So all images have all kind of details. So for instance, let's look for, I don't know. This image here, does it have absolutely all pixels differently? All these are red pixels, they are all the same. All these are blue pixels, they are all the same. So I can use what? You know the answer. Color maps. You use a color map for that. You use a color map. What is a color map now? This is a table. I will write a table. This table will only represent, I will have entries from 0, 1 to 5, let's say. I have 256 possible values. And this is the index of that table. This is the index of that table. And then we have the content of the table. In the content of that table, I will say, okay, if I want to represent Superman, Superman has a red cap. So red is 255, 0, 0. And then it has a blue suit. So now, and this is code 1, this is code, I don't know, this is code 132. And it has blue. So, okay. And now I want to draw Superman here. I want to have Superman here. And I want, this is the cap. Okay. And I want to represent that pixel. So instead of saying this pixel is, this is the cap. So instead of saying this is this, what I say is this is code number 1. If I want to represent the suit here, I want to represent the suit here, I say this is code number 132. So I use only one number. Now I only have a million pixels, a million values. So I have divided the amount of colors by the amount of memory by 3. Okay. There is a price to pay. How many colors can you represent here? How many different colors can you represent in the 2 colors? How many different values? 256 cubed. So 256 cubed. Can you give me a rough number of what is that number? But there is no way. You need a calculator for that. You shouldn't use calculators for this kind of calculations. Okay, so let's see. This is especially when they are power of 2. Okay, so for power of 2, you have to find quick ways. So 256 is 2 to the 8. So this is 2 to the 8 cubed. And this is 2 to the 24. So this is 2 to the 4 times 2 to the 20. Okay, so what is 2 to the 4? 16. What is 2 to the 20? About million. So 2 to the 20 is a million. About a million. So we can represent 60 million colors with 2 colors. These powers of 2 you have to remind. Okay, so 2 to the 10 is how much? This you know, you need to know exactly. 1024. Okay, so approximately 1,000. But this one you have to. And 2 to the 20 we have said is a million. 2 to the 13. Is the product of these 2,000 millions. So this is 1,000 millions, and so on. And what are the names that we have for these? So if these are bytes, what is the name of this? This is not very clear. 1 kilobyte, and this 1 megabyte, and this 1 gigabyte, and 10 to the 14, 2 to the 14. This is the name of that. 1 terabyte, and 2 to the 15 petabyte. 2 to the 16 exabyte. 1 exabyte. Which is not created either. So this is 60 exabyte. Yeah. Okay, good. So then, what are we? We are here, true color and color maps. So with true colors, we can represent 60 million colors. With color maps, how many different colors can I represent? So if I use this table to represent my colors, how many different colors can I represent? This many. 256. So there is a price to pay. So color maps are fine for images like Superman. But they are not fine for images like cats. Even for cats, they don't work so bad. Okay? So there are ways of, okay, I will construct a color map for a cat image, and still it will look like a cat. We will see that at the cost. Okay, any question? No? Okay, so then I will try, if we have time every day, to introduce you to some problems and see how people are solving them. And these are problems that we will not cover during the course. So let's see how let us close this video. Okay, so we get into iPod, and I have taken an example from features that you can see now. Features. So features are something that they are used in a lot of image processing, but we cannot cover everything in our course. So we will have a look at this example now. And by the way, satellites satellite imaging is something that it is very much used. You have seen the Meteosat images, right? So the satellites, they use a lot of different wavelengths to look at the Earth. So this is one of the best examples of hyperspectral imaging. Do you know another example of hyperspectral imaging? You encountered the word today, so you don't know. But there is another one that is fluorescence microscopy. Fluorescence. Gives very beautiful images. Now, so you see in a scheme like this, now you start understanding many of these things. So we have a light source. The light source emits in many different colors. So this is the spectra of that light source. Very typically here you have lasers, you see, and then it goes into the specimen, and now some of the photons are reflected back, and you have a detector here. And depending on what is the laser that you use, you will see. So if I use a blue laser, I will put a blue detector. If I put a green laser, I will put a green detector. And I can put lasers of many different wavelengths. I can put detectors of many different wavelengths. So I can see the same specimen with very different wavelengths. And typically what they do is they mark, they mark, this one. Yeah, we have images like this. So how did they get these images? We have red, green, blue images. And now we understand what they are doing. So they are emitting at 3 different wavelengths. So they have 3 different lasers. They have 3 different detectors. And why do we see some parts of the cell in red, some parts of the cell in blue? What have they used there? Let us remember, let us go back to our drawing. So here's our drawing. Here, our remaining. So this is our cell now. And I want this part to be blue and this part to be red. And I want this part to be blue because this is the nucleus of the cell. And I want this part to be red because it is the cytoskeleton of the cell. And now I have blue light coming in. I have red light coming in. But the red light also comes here. And the blue light also comes here. And you have the key, is in the name, fluorescence microscopy. What is something fluorescent? It emits light. And why does it emit light?
It's reflect.
No. Actually, reflection and fluorescence are 2 different physical phenomena. So reflection is the light bounces, so the photon bounces, while fluorescence is what? You absorb the photon and then you re-emit it, the photon. That is not the same physical phenomenon. So I have both lights coming in, but I have to make these to be red, and this one I have to make it blue, and this one I have to make it red. How do I do it? Red is a cell, so the cell typically would be transparent to light. So my statement is cells are typically transparent to light. So that means that if a photon in general comes in, doesn't interact with data. Some of them interact, very few of them interact. That is why we see cells. But in general, if I want to see that the nucleus is here, the nucleus is blue, and I want to see that the cytoskeleton is here, the cytoskeleton is red, what do I have to use? No, because in general, if I don't do anything, this red photon will go through. Tengo que usar una tinción, pero ¿de qué? ¿Cómo lo hago? De hecho, tiene que ser una tinción fluorescente, porque no se llamaría microscopia fluorescente. Pues voy a poner aquí moleculitas. O sea, ¿qué caracteriza el núcleo? Por ejemplo, la membrana nuclear. Pues la membrana nuclear tiene una proteína. Y esa proteína, yo la voy a marcar. Yo tengo aquí mi proteína. Esta es mi proteína. Pues yo le voy a pegar a mi proteína, le voy a pegar una cosita aquí. Cada vez que se exprese esa proteína, se va a expresar con mi cosa pegada. Se llaman biomarcadores o marcadores. Entonces, me voy a poner una cosita pegada. Aquí está mi proteína, dentro. Una proteína. La proteína de la aquí está mi proteína. Y con mi cosita pegada. Entonces, esta cosita pegada, cada vez que recibe un fotón azul lo absorbe. No es como lo demás. Todo lo demás, lo normal es que no absorban nada. Pero esta cosita azul sí que absorbe y además emiten azul. De hecho, emiten todas las direcciones. Yo los que veo se los van para arriba, se van para abajo, no los veo. Pues sí, a lo mejor depende de dónde ponga mi detector. Si pongo mi detector abajo, pues lo van para abajo. Pero en general la emisión se produce en cualquier dirección. Entonces, cuando la luz llega aquí, algunos fotones los absorberá esta cosita que está ahí pegada y los remite. Y a este citoesqueleto le pego otra cosa diferente. Le pego una cosa que absorbe fotones rojos y que emite fotones rojos. Entonces ahora distinguiré entre el citoesqueleto y el núcleo azul. Aquí han marcado pues, membrana celular y membrana nuclear. Y la otra proteína que está en verde, pues no le puede ser. O sea, alguna proteína que han marcado también. Bueno, entonces, eso. Imágenes hiperespectrales. Hay también en biología. ¿Vale? Y en medicina también hay. Yo conozco mejor biología porque es donde trabajo. Pero en medicina también hay. Vale, este problema. Okay, so this problem is about detecting corners. So can we detect corners of images? So let's say that I'm given this image. This is very cool. Can I run and detect my corners? There are my corners. So you see that it has correctly identified most of the corners there. Let's give a different input. So let's say that I use this input here. Now I will run it. You can upload your own images. This part, if you want to get this extra 1.5%, or not 1.5 point in the score, this is part of the work that. Now what about corners? It has missed a few of them. Or it depends, is this a corner or it is not, or if this is a corner. So how do you define a corner? Now a corner is not so well defined. So do you mean that these are the only corners in the image? Or this is also a corner? And then if this is also a corner, it is missing many of these corners. So it has found corners the background. And okay, this is all of these are not corners. So these are called false positives. These are called true positives, depending on how you define if this is a corner or this is not. But this would be true positive. These are false positives. And these ones here that have been missed, they are false negatives. And there are many true negatives. So there is no corner here, and the algorithm has correctly found that there is no corner. So that is a true negative. Okay, so is this a kind of magic? How do they do that? Now you go to the description of the method. This is the paper, they describe the method. Actually, these people are in Gran Canaria. And they start talking, you would have to go into the details, but they use this sign, nabla of I. Sure that you have had a calculus course. What is nabla? What is nabla? Nabla. So let's say that we have a function I that goes from r squared to r. And we say I want to compute the nabla of I. What is this? Actually, sometimes I don't write the arguments. Sometimes I will do it now. So let's write the arguments. So this is I of R, and R is R squared. Now we will compute the nabla I. This nabla is the derivative of I with respect to x, evaluated at R. I, y. So I told you, thinking of images as continuous functions, it is very useful. So it is only they are only continuous in the real world, but in the computer, it is also mathematically, it is also very good to think of them as continuous functions. So this is simply the gradient. This is the gradient function. This is a function. This is the gradient of the function. And this is a vector. So if this is a vector, I can construct this one times this one transpose. What is the size of that? This is, let's put sizes. Sizes I'm using blue for sizes. So this is 2 times 1. So this is 2 times 1, 1 times 2. So this is a 2 times 2 matrix. But if it has a 2 times 2 matrix, it has eigenvectors. You remember that? It has eigenvectors and eigenvalues. So if you go to the description, of the method, oh, sorry. If you go, it is here. You go to the description of the method. They don't even say what the gradient is. They assume that you know what the gradient is. But they give you, okay, I will construct this matrix. And this matrix has this form. And this Ix is a way to note the derivative of I with respect to x. So I have this matrix, and now they do something with that matrix, and that is how they call